you can prove using something like a sub-Gaussian tail bound, because basically these x transpose epsilon over n, well, this is an average of IID things. And so you can get the 1 over root n concentration. And furthermore, you're taking union, well, you want to bound the infinity norm, so you need a union bound over p things, which is why you end up with root log p over n. And then there will be, well, this factor should show up in your constant, and then I guess the maximum eigenvalue of x should also show up in your constant. But at the end of the day, what we know is that, therefore, we can take lambda to be equal to constant times square root log p over n, right? So we know that any lambda that is bigger than this is certainly fine. And the nice thing is that you can actually choose this. So you don't want to choose lambda to be equal to this because you don't know what epsilon is, right? If you're running a regression, you have no idea what epsilon is. You can only estimate epsilon if you get an estimate of beta and then take the residuals, but that's bad. But if you know that you should just take a lambda which is equal to something like this, then, well, you know what p is and you know what n is. So you don't necessarily know what C is. So C, no, I mean, this is also like a research question, right? So the problem is that C needs to depend on this unknown, variance, and also on the unknown variance of the x's, right? And maybe it's okay to say that you know something about an upper bound on the covariance of the x's because that's your design. But then the error is a problem because you might not actually know how big your error is. So there's sort of a big, there's another branch of high dimensional theory where people try to do not Lasso, but solve a different program, minimize something else that will give you a choice of lambda where the constant doesn't depend on sigma epsilon. Or there are other methods that people have for adapting to your data. So they try to solve Lasso for one choice of lambda and then do some kind of comparative analysis and figure out the right choice. Okay, yeah. This log p here? Yeah, so basically what you want to do is you want to say that with high probability, you want to say that with high probability, epsilon, canonical basis vector ej transpose x transpose epsilon over n is less than or equal to t for all j between 1 and p, right? So if you want to bound this by t, then you need to bound every single component by t, right? Because this guy itself, this is a p-dimensional vector, right? Because this is n by 1, this is p by n, so it's p-dimensional. You want the infinity norm to be bounded by something, so you need to bound everything independently, and then use the union bound. That gives you log p. Yeah. Okay, great. So what do we have at the end of the day? Well, at the end of the day, we look at that inequality up top, and we plug in lambda. We plug in lambda equals this guy. And so, therefore, with high probability, and now it's with high probability over the randomness in x's and the randomness in the epsilons, we have beta hat minus beta star, 2 norm, is bounded by, I guess it should be 3 over alpha times square root of k times some constant times root log p over n, which is equal to 3c over alpha square root of k log p over n, right? And so this should agree with the picture I had earlier, which was, of course, not just for Lasso, but the non-convex case. Even that fell asleep. Okay, well, it will hopefully wake up, right? Yeah, it's flashing, right? Right. So this is what we have for Lasso. Okay, so this is all great. Yeah, right here, right? That's where the rate is coming from. Okay, this is all great, but the problem is when it's non-convex, then everything kind of goes out the window. Yeah. Okay, so right. So where we used the convexity was that we wanted to say that in order to deal with beta hat is a global optimum. So where we started from was this basic inequality. We said that you evaluate your objective at beta hat, and it's bounded by your objective evaluated at beta star, and then you rearrange everything. Now, if we start talking about non-convexity, then actually the trick is that we want to work with this instead. So we don't know that the objective evaluated at beta hat is bounded by the objective evaluated at beta star. All we know is this first order condition. And the magic is that, in fact, this sort of theory goes through by using this, by starting from that inequality instead. Okay. But I guess I'll get there, or I'll get to some version of that. Right, so a good reference for all of this Lasso theory is a book by Bielman and Van de Geer, which, I mean, well, they prove some instrumental results in this area, but they also have many references to where some of these results first appeared. Okay, so now we move on to non-convex case. And the question is there actually any hope? So at first we thought that, so to back up a little bit, we kind of stumbled upon a proof that these things work in the case of errors in variables. So if you remember, my errors in variables story was that I had x's and then their modified disease, and then we just have an L1 norm. All right, so sort of if you stare at these inequalities long enough, then they work their way out, and then it seems like you can end up with some kind of a result that says that local optima are all well behaved. Okay, so then we were interested in asking, well, what if the regularizer is something like a SCAD regularizer? Okay, and then we started thinking, well, I don't know, can you really say anything about how local optima are well behaved? But the picture that I had in mind was that, so what I have here is this is our wiggly non-convex function. Okay, so it might come from errors in variables loss, it might come from a SCAD regularizer. And actually, earlier I wrote ln plus rho, so think about this as ln plus rho, that's my wiggly function. And if it has local optima that are kind of everywhere, then that's bad because they're not very close to each other. Okay. But what we do know is that in expectation, this black curve is equal to something that's nicely behaved. So maybe let me explain that with a little bit of a picture here. Okay, so if we use our errors in variables regression, then what was that? That was we want beta hat in arg min of beta transpose, and then we had our not convex thing, and then we had something else, y transpose c over n beta plus, let's say, the L1 norm. Right? Okay, so this is my not convex quadratic. But in expectation, this thing converges to sigma x. And then we have a nice convex thing. Right? So that's the red curve. Similarly, if we look at SCAD plus ordinary least squares regression, then what's that? Well, that tells us that we have beta hat in arg min of beta transpose x over n beta plus y transpose x over n. There's probably a 2 missing. Let's just put that in here for good measure. Okay, and then we have some lambda, some rho sub lambda of beta. Right? Okay, so this part is convex, although it has 0 curvature in some directions. But in the limit of, if n goes to infinity, then it has nice positive curvature everywhere. This guy is a bit more problematic because remember that the SCAD regularizer looked like this, and it had negative curvature, and then it became flat, right? But if we think about taking n to infinity, then that doesn't affect this because this is just a regularizer. But this thing will now have some nice positive curvature in all directions. And then this one has some bad negative curvature. It's like negative mu, right? But the nice thing is that the sum of the two is actually going to be nicely convex. Okay, so then we can think about this picture as that's interesting. Maybe let me reload this guy. All right, view full screen one. Okay, well, we'll figure it out. I guess we'll take a break soon anyway. Okay, so the idea is that this red curve here will be the sum of the alpha that's dominating the mu, right? Okay, so what's the nice thing? Well, the nice thing is, so this is a bad picture, but now imagine that we're arguing from the point of view of the gradient. And why do we need to argue from the point of view of the gradient? Well, as I said, all we can start with is that first order stationary condition. Okay, so if we were able to argue from the point of view of the gradient, then the gradient of a nice convex function is some monotonically increasing function, and it's, let's say, strongly convex because alpha is dominating mu, and it intersects the axis at exactly one point. And then now we think about this wiggly black curve, and if we had some good behavior at the level of the gradient, then what would happen is that this gradient of the wiggly black curve would be sort of close to the red curve. And then the nice thing that we could wishfully hope for is to argue that if we have sort of uniform convergence in some sense, then any crossing point of the black curve with the axis is going to actually be close to the crossing point, this beta star. Right? So this is the true beta star because the true beta star is the minimum of the actual convex thing. And now the idea is that there might be more local optima, but they're all kind of clustered together. Yeah, questions?
Just like stochastic gradient, where, for example, if they come to that, you can assume that your red curve is just a sample. And this is why you will have the line. Because you just calculate the red curve.
I'm not sure that I understand the connection. I mean, so this is not actually going to be the integral of that one, right?
No, I'm thinking the fact that you say, for example, y, when you have this d, right, and you say the vector of f.
Right.
So what you should do is basically you sample a lot of times z, you take the average as point to get closer. So if you just take one sample, you just get
but we're not taking one sample, right? So we are taking n samples. The thing is that we're not taking enough samples to make everything convex.
Okay.
Yeah.
Would it make sense to just come up with these envelopes that are convex to both sides and solve that?
Well, so I mean, I guess like so you're saying that if you had some kind of shape like this, then you're thinking about doing some kind of convex envelope. So there are different types of convexifications that you could do. For instance, with errors and variables regression, where you wouldn't be solving this, but you would be solving some, let's say, convexified version, and things like that would work. But I guess what this theory is saying is that even if you don't bother doing any of that, then you can still just walk in your non-convex landscape and not worry about anything. And I think, yeah. You would need to iterate until convergence, but only from one initial point. Yeah. So I mean, doesn't any local optimum you find is okay, right?
So you don't get stuck at the beginning.
No, because basically the shape will not be like that, but it'll be like this. So if you were to unwrap this good behavior on the right side, take the integral of that, then you'll find that all of your wiggly points have to be close to beta star, right? Okay. So yeah, this was just that's the way that we thought about it, and realized that yeah, maybe if you just argue from the point of view of the gradient, then there are conditions you can put on the gradient so that they ensure good behavior. It's back. Okay. All right. So here's where you need some kind of curvature fighting against the negative curvature, and then this restricted strong convexity, which generalizes the restricted eigenvalue condition, and I'll go into in much more detail, actually controls how quickly the black curve, the gradient black curve is converting to the gradient red curve. Okay. So now let's talk a little bit more about what these conditions look like. So as I said, the most salient ones are this sort of curvature, restricted strong convexity, and then a bound on the negative curvature. And let's just skip over that right now. Okay, so this slide is it's the definition of what the restricted strong convexity condition says. So it's just a condition about your loss function. And I think it's worthwhile to illustrate what this looks like for the quadratic, for the least squares loss function. So let's erase this over here. Okay, so let's imagine that we're looking at ordinary least squares. And ordinary least squares is the loss function ln of beta is equal to 1 over 2n times y minus x beta 2 norm squared, right? So that's the loss function, then we put a regularizer and we minimize that. So now we want to look at the gradient. So if we look at the gradient of ln, then that's equal to 1 over 2n times, well, the 2 cancels. So we have an n here. We have a y minus x beta, and then we have another negative x transpose. Right? Okay, so now we want to plug in these guys. So the left-hand side of that thing is equal to negative 1 over n times, well, okay, so the first term goes away, right? So this is just evaluating it at beta star and beta star plus delta, so this first term is just going to go away. And so what we end up with is x transpose x over n times delta, right? Because that's just the difference between beta star plus delta and beta star and beta star. So then we need to multiply that by another delta. Okay, and this is something that looks familiar. Delta transpose x over n times delta. Okay, so we can see that the restricted eigenvalue condition, it's generalizing restricted strong convexity is generalizing what restricted eigenvalue is telling us. Stuff on the right, let's not worry too much about. So essentially, if I cover up this second term, then it really does look like the restricted eigenvalue condition. I want it to be bounded by alpha times some 2 norms squared. The reason why there are some other terms is that you need to remember that we only need restricted eigenvalue to hold in certain cone directions. And you can argue that that in these cone directions, the L1 norm is bounded by the appropriate constant times the L2 norm. So you actually do get, let's say, a bound on this thing of alpha half times the 2 norms squared. Okay, so the restricted strong convexity condition was introduced by Negaban et al. And the reason for studying that at first was not to look at non-convex problems, but to look at things like logistic regression. So basically generalizing the theory for the Lasso to L1 penalized whatever you want. So logistic regression, graphical Lasso, or lots of other things. So they came up with a condition that was both nice to state and also easy to check, or easy. So if you use the right techniques, then you can show that these things hold with high probability. And our contribution was to tweak the definition a little bit to allow there to be negative curvature in some direction. So I think that the condition from Negaban et al. Probably just had this first expression didn't have any bound in R or anything like that. And what we were able to show is that if you allow yourself to have some negative curvature in some directions corresponding to, let's say, these measurement error models, then you can verify these conditions hold, and you can also verify that they're strong enough to guarantee the consistency of local optima that you want. Okay. And then I guess I'll take a break in a moment, but for the regularizer, I don't want to go into much detail. There are conditions that you need. You basically need the subgradient to be bounded, and you need it to be not too non-convex. All right. So I think this is a good time for a break. So let's take a break, and then I will give you the highlights of how you use restricted strong convexity to get to consistency of local optima.
So we meet at 10:20.